Open my camera. Okay, guys, this week we're gonna keep discuss the regular languages, and this is the part 2. And this part 2 we have the regular expressions and non-regular languages. So I would like to start with like what we mean by like expressions. Like for example, this is like one of the like well-known expression using the math, right? Usually like there are parentheses, like each element has a meaning, right? There's nothing like for just there for fun, right? Everything has a meaning. For example, the parentheses just declares the priority. Summation operator is there, like we know what does it mean. And by parentheses, we know that we have to calculate the summation first, and then the multiplication operator, another operator, right? And there are operands. In this case, there are numbers, right? So we know what these expressions mean, and we know how to solve it. And so this is like very straightforward. And we hear the same thing with our languages as well. Okay, guys. So we have the union, the concatenation, and asterisk operator, right? Asterisk is the power, right? And we use the like regular operations to build up regular expressions. Okay, guys. Here, did I give it? Yeah. So let's look at this expression like in close. What we're gonna see is that like this 0 and 1 is just the shorthand for like the language, which is 0, or set which is 0 only contains 0, and the set only contains 1. So they are like because they are the language, not just the one character. With this parentheses and union operator, we can say that this is what we need to do, right? There are two languages, and we apply the union for these two languages. And this is also meaning that like we have this language 0, and we can do the asterisk operator or star operator to the 0. And this entire thing is simply shorthand for this one, right? Set 0 or language 0, union language 1 in parentheses. Then we do the concatenation with the 0, language 0, and the star operator. So why do we need these regular operations? And let's see what I mean by that. Okay, guys? So basically, regular operations are just like the shorthand or mathematically specifying the languages. Okay, guys, let's look at the formal definition of regular expression. So R is a regular operation if R is A for some A in the alphabet sigma. Right? That's very simple. If there's some alphabet in the sigma A, then the regular expression should be A. Also, if there's a epsilon, which is the empty string, then regular expression should be empty string. And also, regular expression should support the nothing, like empty set. So this is empty string, this is empty set. There are two differences. There's a question in the quiz, and the answer is that the epsilon is the empty string. Like you can assume that there is a, let me show you this way. So the difference between like the empty string and empty set, like this is the Q1, let's say AB is going to be easier for me. A, B, and we can go from A to B with the epsilon. I think, but not reading anything. But empty set means that empty set, there is nothing, Epsilon is something. It's just empty string, but empty set is nothing. There should be nothing. So, and you can see like the rest of it, and you can read the formal definition, but this is what we call this is the formal definition of the regular expression. Okay, guys, and like as I said, like A and epsilon are just represent the language, not just the letters. The language of take meaning combination. And also like regular expressions, we use regular operations to build up regular expressions. So if they support these three regular operations: union, concatenation, and star operator. So let's look at some of them. Okay, guys, let's look at some of them. For example, this one, first one. Okay, guys, just focus on this first one. Can I zoom in? Yeah. So let's look at the first one. It is 0 star 1 0 star. What does it mean? It is like any language, like language accepts all strings which contains a single one. So there should be only one, right? How can we see that? There's like any number of zeros, right? And then we receive a 1, and then we can say any kind of a number of zeros. So how we can draw the DFA for this thing, for this language? Like we have the starting thing, right? We have zeros as many as we want. This is A. And we have only one B, only a single one, right? And we go to B, which is the accept state, right? It also receives all zeros. But if we receive any other one, right, it violates the language, it violates the rule. So we cannot accept this state. And then it doesn't matter how we zeros or ones. Right, guys? So I define like if assume that we have only 0 and 1 is a language. In our output, we have only 0 and 1. So this is how we show it, right? We can receive as many as 0 as we want, so we can state A, but we can't accept it because we need a string contain only one single one, right? Only a single one. So we can stay here with all zeros. When we read a 1, we go to B, which is accept state, and we accept the string. For example, 0, 0, 1, right? This is acceptable. Also another 0, this is also acceptable. So we can, after receiving a 1, right, we can read as many zeros as we want. It doesn't matter. Right? Whenever we see the second one, we cannot accept it, so we leave from the accept state and we go to the next state, which is C, and there is nothing. Right? We cannot go back to B to accept because like we read the second one. Okay, guys, let's get the second one, the second example. So this sigma operator means that like all the letters, all the alphabet, all the letters in our alphabet. Okay, guys. So this says our language accepts strings that has at least one, right? Is this clear? We make sure that there's only one, and we enforce it. But before and after, we can say we can have as many the other characters as you want. So this is also like the content string 001 as a substring, right? The third one. Again, we had 001, we enforce it as a substring, and before and after we can have whatever we want. It doesn't matter because like the rule says that we just want to see 001 as a substring. So this plus sign is here. Oh. Okay, I think I should go back. Okay, 25. Okay. So this plus sign, guys, is shorthand for like the R star. It basically says that like R star means that like we can have 0 R, right? Or like as many as we want. But plus make sure that there's at least one R, one character, you know? So plus and star are different, and plus make sure that like there's at least one character in our like power. So here, what we are seeing that this is like the rule says every 0 in W in our string is followed by at least one. Is that clear? So when we see a 0, there should be a 1. So 0 is violating the rule. You know, we cannot have a string that contains 0 substring. Because we say every 0 in our string is followed by at least one. So we can look at the others one. I'm gonna skip it. So any question about those stuff? Okay. So there are some rules. Okay, guys. If we union with an R, R, let's say in a regular language, in a regular expression. With empty set, the answer is R, because this is empty, right? So you have R and empty set, right? This is empty set, there's nothing. If you just union, then you got the R, because this is empty set, there's nothing. So if you concatenate R with an empty string, right? You have R, you add the empty string, you basically merge these two, but there's nothing. This is empty string, so the answer is R as well. But there is one catch. If you have R, right, union with the epsilon empty string, this is not equal to R. Okay, guys. And if you try to concatenate R with empty string, the answer is not R, but empty string. Okay, guys. So I think I asked you a question about this thing, so I'm just skipping the definition or why we are doing that. So this is going to be your assignment. So I want you to explain why. But the thing I'm not sure about this thing, why there is 0. I think it should be. I think it should be an R, not 0. My typo. I will look at it. Okay, there's no assignment. I will look at it and I'll let you know. I make an announcement and I explain this thing. But this one, the second one, I will explain the second one. So this is the concatenation, right? So we have the R, the regular expression, and we try to concatenate with empty string, right? So you can say, okay, this should be R because like there's nothing, so we concatenate this thing, you know, we just add these two things, and there should be the answer should be R, but it's not, because like since there's nothing, you know, you cannot do you cannot perform concatenation over nothing. So it's just like you can assume that it's like the in multiplication this is a 0, you know, it just says there's nothing to do, so the answer is like nothing. But I'm not sure about this one. It should be R. I will check it and let you know. Okay, guys. There is no question about this thing. So, and the reason we see the regular expressions actually like because they are equivalent with the Python automata. You know, by being equivalent, they are equivalent in their descriptive power. So, which means that a language is regular. You can only if some regular expression describes it. So this is why we're learning about regular expressions. So if there's a language, we should be able to describe it, the regular expression. Or it is vice versa. If something is regular expression, it expresses a regular language, right? So this is like two ways. So yeah, if a language is described by a regular expression, then it's a regular. If a language is regular, then it's described by a regular expression. So we look at each of those. Like we try to prove these two things, right? Because like we do this claim. So we learned this regular expression because we said they are equivalent with the Python automata. So how? Let's look at the first one, I think. Yes, if a language is described by a regular expression, then it is regular. So guys, like this is, let's say this is P, I'm sorry. Then it's regular, this is P. If something described, this is Q. So this thing like P, like this arrow, right? Two-sided, and Q. Okay, guys. And we can separate this thing as like part space, like we can write this thing P is Q, or P is Q, right? This way. Okay, guys. So we look at each of them. So if a language is described by a regular expression, then it is regular. So to do that, the proof idea is that basically we show how to convert a regular expression into an NFA, because we know that, right? Because we know that NFAs are regular language, NFAs recognize regular languages, and if we have a regular expression and we can convert a regular expression into an NFA, non-deterministic finite automata, then you already showed that NFA describes a language, right? A regular language. So then we should be fine, right? This is the proof idea. So we have this thing, if you remember, the formal definition of regular expression. So we look at each of them, each of the what do you call, not choices but options, no, each bullet point, let's say, each bullet points we'll investigate individually. Okay guys, let's look at the first one. A, for some A in the alphabet sigma. This is very simple, right? We have, it should be the language A if there's alphabet A in the alphabet sigma, letter A in the alphabet sigma. So we convert this A, right, in a NFA like this. So this is the language that accepts A, right? Start from the start state, receive A, and accept it. So this is an NFA, right? And this shows that the regular expression A. Is this clear? How we convert the regular expression A to the NFA for the first one? And second one is empty string, right? So I think you see the difference between the empty string and empty set right now more clearly. And empty string, we accept empty string. If there's nothing, then we accept it. You see that, guys? Start state and accept state is the same thing, and there is nothing to read to accept. If we have anything, like we need to go different state with sigma, and we can accept this thing as a sigma. This is, let me put this way. So this is the sigma, right? You see that? We accept only nothing. If there's no string, we accept it. If there's any kind of input, then we go to different state, which is not accept state, and we can just read all the other alphabets there. And there's no chance to go back to accept state. So what about empty set? Is this. There is nothing to accept. Okay, guys. We start, there's nothing to accept. You can assume that this is like this. There is a sigma. You can be there, but there is no accept state, which is the empty set. So this is the difference. Empty string, there is nothing, then we accept it. Empty set, there is nothing to accept. I hope this is gonna be like much more clear for the difference between the epsilon and sigma, epsilon and the empty set. So if you remember, like the last week, I left this part to you, you know, like I asked you to read this part and understand like the union and how we prove that thing, right? Remember this stuff? So it's called V equals under regular operations, and this is like how we convert the union operation into the what you call the NFA. Okay, guys. So here we have one set and one, we have another set and two. If you're gonna perform the union, right? How we do it? We just have the start states, and we just have the empty string. Connect them to empty string. Then we have the union. So this is how we basically convert the regular expressions which has union into the NFA. Is this clear? Like what union do? Union basically do A union B means that if a string is acceptable by A or B, then we accept it, right? It doesn't matter which one is accepting. So here, let's say this only accepts the only one, this accepts only zeros, you know? If we have only one, we can go here and accept it in one of the state. If this is only zero, we go this thing and accept it only zero. So this is it. If you see, this is the same stuff. Only difference is that like we have the start states, we connect start states with a different start state, and then we just provide the empty string. And the other thing is the concatenation, right? This is the fifth one, I think. Yeah, fifth one. So this is the concatenation operation. You know, get N1, N2. So concatenation does something like that. We have A, concatenation B, and we accept the strings which first accepted by A, and then the rest of the string, the second part of the string must be accepted by the B. So how we do it? Basically like this. We have A and 1, we have N2. So from the accept states, from the N1, right, we have the epsilons, empty strings, to the start state of the N2, right, like this. And then we remove this thing as a start state, accept state, right? So we start from the N1, we reach the accept state of the N1, then we have the epsilons to go back to transition to N2. Then at the end of N2, we keep the accept states. Is this clear? So our new language accepts a string, which one part is accepted by A and the rest is accepted by the B. Is this clear, guys? And this is how we can convert a regular expression into NFA by if there is a concatenation. And the third one is the star, right? Star operator. And this is very straightforward, I think. We just define a new start state, and from the accept state, we just go back to our start state. This is clear. Why we are doing this thing? Why we have another start state? Because the start can be 0, which means we accept no string. Right. Therefore, we just put this thing, we accept this thing, accept the empty string, and then we have epsilon to go back to the original start state, and then n can be repeated as many as we want. Okay, guys. So there are some examples. Let's look at how we can convert this regular expression into NFA. So we have A, we have B. They are straightforward. How we can concatenate A and B? By applying this empty string like this, right? From accept state, we have the epsilons. So from the A accept state, we have the epsilon to the B, right? This is AB. So there is, remember, from first start, there should be like the concatenation. This is just shorthand. Okay, guys. For the union, there's an A as well. Like this is the A. For the union, we go back to this one, right? And apply this thing. So this is the AB part. This is the A part, and we apply the union operation. For the asterisk, for the star operator, again, we perform this, right? We define a start state, which is accept state as well, and it's accept the on empty string. And then we do like what we supposed to do here. Is it clear, guys? Another example. So you can look at this one. Like there's a union, then star, then the ABA part is like another concatenation, and then we do the concatenation with this star. Just look at it and analyze how it is performed. So we explain this one, and second one is the other way of the second way of our claim, our theorem. If a language is regular, then it is described by regular expression. So this is different, right? If a language is described by regular expression, then it is regular. So this is the opposite way. It's the other way. So let's look at how we prove it. So if a language is regular, it is accepted by DFA. That's correct, right? So we describe a procedure for converting DFAs into equivalent regular expressions. Then we can prove this thing, right? So to do that, we define something like GNFA. There's something new, but it is like the easiest way to do that. Okay, guys. So you are seeing a GNFA. It's called a generalized non-deterministic bind automata. So this is the NFA. There's nothing fancy, but the transition arrows, you see transition arrows, they don't have the letters, but they have regular expressions. This is the only difference between NFA and the GNFA. Also, like we had some specification to make GNFA like understandable because it looks so complicated, you know, and there are some rules. We have 3 rules, 3 conditions. So to say the first rule says the start state has transition arrows going to every other state, but no arrows come from the other state. So we have our start state must be connected to all other states. You see, this is connected, this is connected, this is connected. This is the first rule. But there is no going back arrow. You know, we cannot go back to start state with any arrow. I hope it's clear, guys. So this is the first specification. So we have these rules to make things like easy to understand. So there's only a single accept state, right? And it has arrows coming in from every other state, but no arrow is going out. You see, from every state, we have an arrow. Is this clear, guys? Accept state, but there is no arrow going from the accept state to another state. There is no arrow like this or like this. So start state, there's arrows going out from start state to all other states, but from accept state is different. There are arrows from going in from every other states to accept states. And the other rule is that the accept state and the same start state cannot be the same state. And except for the start and accept state, one arrow goes from every state to every other state and also from each start itself. So there should be arrows going in, going out, and also this way, you know, like from self-pointing arrows. Except start and accept state. Okay, guys, all other states must have going in and going out arrows, and then the self arrows. Okay, guys. So there's a formal definition of it. Again, Q is the final set of states because we have the final set of states, and sigma is the alphabet. And transition function is different, right? Q accept times Q start, and R is transition function. So we have only one start state and we have only one accept state, and these two must be different. Okay, guys, you can look for more details if you're interested in. So how we can convert a DFA to GNFA? Okay, guys, if we have DFA, so what we need to do, we just need to follow these four things. Do I have an example? Yes, I have an example. So let's skip this part so because we can go back there. Okay, but first, so the idea is that we want to convert the DFA to regular expression, right? So what we do, we first DFA to GNFA and then GNFA to regular expression. So we just do the second part first, and then we go back to the first part. So here, the idea is that we reduce the states only two states left, the start and accept state. And the arrow between them is the regular expression. Okay, guys, let's look at this one. So this is a GNFA. This is just not GNFA, this is just the NFA, right? And we just show how we can reduce the arrows from QI to QJ. Okay, guys, so first here, we have R1, right? And then with R2, we can have as many as R2. And then we have like the R3. This is the first part. Then we can reach the QJ. Second part, since there are two different entities, we can, like two different languages, we need to apply the union. And then with R4, we also reach the QJ. So instead of like these three states, 4 arrows, we just have 2 states with the like one arrow. You see? So this is like these two are equivalent. So this is how we reduce the number of the. This is how we reduce the number of the states. These are equivalent. Okay, guys. And for DFA to GNFA, we need to apply like the 4 rules, you know, at the top. And there are some examples. If you remember, the first rule says that, right, we have the start state, right? So, an empty state, and the start state and the accept state. These must be 2 different states, right? And there should be no incoming arrow to start state, right? And all state must have the outgoing arrow to the accept state. This is what we try to do. Okay, guys, if you look at these 4 rules, you know, we just follow this thing. It says like add a new start state with an arrow, epsilon, to the old start state. Like, this is the first step, right? We add a new start state to the old start state with the arrow, epsilon. So this doesn't change anything, right? This doesn't change any kind of descriptive power of this start state. And here, add a new accept state with an arrow from the old accept state, like this. Like this is accept state, and now we have new accept state with the arrow, epsilon arrow, right? If any arrows have multiple labels, we replace each with a single arrow whose label is the union, like this. If you A and B, we put A union B. And then we can perform the state reducing thing, right? Instead of like this B, A union B, right, is a star, we can just say B, A union B, star. And we can get rid of the second state. Is this clear, guys? And this one, also we can get rid of this thing because like this is A star, right? So A star is gonna be the concatenating, right? A star B, so A star coming behind front of this regular expression. A star B and A union B star. So this is the equivalent GNFA. You know, from this DFA, we generate this by applying this 4 step, you know. This is another example. I ask you to do that. I ask you to analyze this thing. And now non-regular languages. Is there any kind of question about like the previous stuff? Okay. So non-regular languages, why do we need that? Because like we always talk about like what we can describe. But to understand the power of something, you just talk about like to their limitations, you know. So there are some languages that no DFA can recognize it. For example, this language. So we cannot define this language with a DFA. If you're able to do that, then you're gonna be like, we can win the Nobel Prize. And this is just like prove that. This is proven thing. So this is ON, 0n to the 1 to the n, if n is bigger than 0. Remember, because like, the problem is that we need to remember number of zeros, you know. So there is no DFA can do that because we need to remember number of zeros. Okay, guys, just try to draw it. You cannot do that. Like, you can have zeros here, you know. Okay, you do like, let's say 10 of zeros. Then how you can just enforce like this one to be exactly 10 times, you know. Since the n can be like the bigger than 0, so we cannot solve it, you know. So another example is W like has an equal number of zeros and ones. Is this really an equal number of zeros? I think this is non-regular, but this is regular. Has an equal number of occurrence 0 and 1 and 1 0. So this is regular. I think so. Why I didn't have this? Oh, okay, okay. So guys, this is non-regular language because like equal number of zeros and ones, so we need to remember number of zeros and ones, but this is different. This is different, and this is, there's a assignment about this thing. Why this is not regular, non-regular. So this is regular language. You can remember the number of 0 and 1 zeros. Okay, guys. I'm confused. Okay. So to understand if the language is, I think I have to stop here because there's so many things to talk about. Okay, guys, I'm gonna do another video. Okay, because this is important. I'll record the video and let you know this part starting from 46. Okay, guys, I cannot give you this thing as I'm told. This is very important. So, as you see, I want you to, as assignment, read this 3 example from the textbook, and problem set 2 is out. So you have 1 week to complete the problem set 2. And as I said, like I'm gonna record the video explaining the pumping lemma. This is the way how we differentiate between like the distinguished non-regular language from the regular languages. This is how we use it. Okay, guys. And let me see. So problem set 2 is out. Due date is like next week at 8 a.m. So you have to answer those questions starting on page 83, and there's only one part 2. Okay, guys, I give you a language which is just AB, and I want you to show that if A is regular or non-regular language, and I want you to show the proof, do the proof. Okay, guys. So actually, there's something missing. Okay, guys, I want you to do this thing as well. If this is regular or non-regular, I think this is regular, but I want you to do the proof this thing as well. So I'm gonna do that part 2, like change this PDF at this thing as well. It'll be like the part 3. Okay, guys. Then you can do the problem set 2. Any question? Okay, then I'm gonna stop the record.